we're going to start by looking at what an eigenstate and eigenvalue really are. And then Monday, I think, is when we're going to start using some of the matrix notation with eigenstates and eigenvalues, or matrix calculations with eigenstates and eigenvalues. But for starters, just the terms. Eigen is translated differently depending on who's translating it, either as the one or its own. And an eigenstate, eigenvector, or eigenfunction, they all mean the same thing. So eigenstate, eigenvector, eigenfunction, all pretty much the same thing. And an eigenstate or eigenvector or eigenfunction will have associated with it an eigenvalue. The eigenvalue, I was calling my contact here because I was worried that no one was answering there. That was like the third or fourth call that you finally answered. So she saw that I called. She just came to check on it. So you have an eigenvalue that goes with an eigenstate, one value. Now, yeah, here's those words again. And stationary state, one more word that doesn't have eigen in it, all refer to the same thing. So it can be confusing when you hear eigenstate, eigenfunction, eigenvector. You're like, which one's which? There is no which to it. They're the same thing. And stationary state is the term I probably should have been using up to this point, right? When we found our solution to the Hamiltonian, we found that there wasn't just one solution, that there were a number of solutions, and each one of those was a stationary state. Now that I officially am introducing the word, now I can call it an eigenstate. And something that is of actually pretty good importance is the word degeneracy. Degenerate does not mean base or evil or anything like that. Degenerate means that you have multiple states that give you the same eigenvalue, right? The eigensystem, you have one eigenvalue for one eigenstate. So one eigenstate can't have multiple eigenvalues. It can only have one. So you say you're measuring the position. If you're in this eigenstate, you're going to have one position. Let's go to position is not defined by your eigenstate from what we've learned. Energy, right? Because we found the eigenstates to the energy operator. And so each eigenstate to the energy operator has one energy. If I change to a different eigenstate, then I would have potentially a different energy. But if it's degenerate, I could have three states that all have the same energy. So that's where degeneracy is. You have different distinct states that can have the same energy. On the other hand, it's impossible to have different energies in the same distinct state. So some properties of the eigensystems, and these are actually all things that we've already learned. The eigenfunctions correspond to different eigenvalues, and each eigenfunction or eigenstate or stationary state or what was the last one? Eigenvector have to be mutually orthogonal so that they will span all space, the things that we've just learned about, like when we talked about Hilbert space on Wednesday. And so the eigenfunctions of the Hamiltonian form a complete set, meaning that they span all space, and the eigenfunctions can be normalized. That means they're square integrable. Now we're going to see an example real soon that's not square integrable, and then we'll talk about that some more. But it's not in Hilbert space then. Here is your basic eigenvalue relation. You have operator acting on eigenstate equals eigenvalue times eigenstate. There's nothing there that is new to you at all. But now we're getting the terms and being very formal in what that means. And so we can simply rearrange this to operator minus eigenvalue in parentheses times the eigenstate is 0. When we do stuff with matrices, that's exactly how we're going to solve them. We're going to rearrange it like this, and with the matrix, we'll then find what the eigenvalues are in some intermediate level linear algebra work. Of course, we've already solved this. We solved this with the Hamiltonian. We used the Hamiltonian, the energy operator acting on an eigenstate is equal to the energy value times the eigenstate. So the stationary states corresponded to eigenvalues of energy because it was the energy operator. Now let's shift to something that's more interesting. We found the eigenstates for the energy operator. We should be able to find the eigenstates for other operators as well. So let's find the eigenstates for the momentum operator. So the momentum operator, I noticed it down here. I didn't notice it here. In one dimension, I'm just going to use a regular d. So I have momentum operator is minus I h bar d dx. And so using our eigenstate relationship, our operator acting on our eigenstate should be equal to our eigenvalue times the eigenstate. So keep in mind here, the regular P is the value of momentum. This gives us a differential equation. How do I solve this differential equation? Which I will write. There is an easier way of writing it. It looks less cluttered.
You could bring f over to the left by f, and then bring dx over to the right, and integrate both sides. Yeah, separation.
That's exactly correct. So we multiply both sides by dx over f so that we will have the dx's cancel on the left side and the f's cancel on the right side. And actually, I'm going to divide both sides by minus I h bar as well. And so that gives me df over f is equal to ip, being on the line is not good, ip dx over h bar. And then we have the left side is a function only of f, even though f is a function of x. The left side is only a function of f. And so I integrate each side independently, and I have natural log of f over f0 equals ipx over h bar. And the last step then is take the exponential both sides. F is equal to f0 e to the I px over h bar. So this there's another way of writing it that's made a little more explicit. That is the eigenstates for the momentum operator. Now, I said it's eigenstates. It doesn't look like eigenstates, does it? It looks like one equation. So why would it make sense for me to call eigenstates is this equation?
Because it's a variable function we can change with x.
Because P, the momentum, is anywhere between minus infinity and plus infinity. And so this is an infinite number of states. of continuous states. Not discrete states, but continuous. And then there's the big question. How do I normalize this baby? If it's an eigenstate, it's got to be normalizable, right?
Right. Fx. Yeah, on fx.
That's the normalization condition.
Right.
I'm going to write this first as F1 and F2. So that's not actually normalization anymore. What should it be if it's F1, F2?
What?
If instead of doing normalization, I want to do something different here for the calculation because it makes it a little clearer. If I put F1, that is state 1, so F1 means I have momentum P1. So if I have F1 star F2, what is that actually going to be? What should it be?
What that should. What was the question?
Okay. Yeah, I need to back up because I think I lost you on it. So instead of doing the normalization was integral from minus infinity to infinity of psi mod squared equals 1, right? That was our normalization. But we had another situation that was or to be more we had this. What was this condition called?
The Kronecker delta.
Yeah.
Wasn't it like Dirichlet's theorem?
Dirichlet? No.
Yeah, that.
No, it's not Dirichlet's. Dirichlet's theorem is applying Fourier transforms.
Well,
it's similar to this one, right?
It's like that.
If n is equal to m, then what is the Kronecker delta?
1.
1. And if n is not equal to m, it's 0. Okay, so that is our orthogonality relationship. The fact that this has a 1 implied in front of it means that this is our orthonormal relationship. Because it's including both orthogonality and the normalization condition. Now, to make life a little easier, that's the way I want to start this. I want to look at the orthonormal relationship. So I'm going to look at the integral of F1 star F2, or being even more general, Fn star Fm dx. So using the definition that the n is just labeling what the momentum is, that would be the integral from minus infinity to infinity of F0 star e to the minus I p sub n x over h bar times F0 e to the plus I p sub m x over h bar dx. Right, I've just put in Fn and Fm. Bring the F0 mod squared out front. No need to keep that in my integral. And the exponents have I, x, and h bar in all of them. So I'm going to put e to the I parentheses pm minus pn over h bar x dx. So that's the integral that should give us our orthonormal condition if it's truly a solution. And now, when I looked at this last night, it was late at night. Dr. Hansen stays up later than me for sure. I was dying from lack of sleep. It was 10 o'clock my time, 11 o'clock yours. I sent an email. He replied instantly. Makes me feel a little insufficient. If we look here at equation 2.144 on page 77 of the textbook, it has the key that I finally figured out to make me so I could go to sleep. So what does that say? That equation says that the integral of 1 over 2 pi minus infinity to infinity e to the I kx dk is equal to Dirac delta x. Now I'm going to take that relation, fail. I'm going to try to have less failure and more success. And I'm going to apply it here. So using this relation and trying to find a comparison, you can immediately say, well, I'm going to, first of all, that was I kx dk. Let's just change the k and x. It's going to have to be the same if I just change the x for a k, because they're just variables. And so the integral of e to the I kx dx from minus infinity to infinity, let's multiply both sides by 2 pi. What do you say?
That works.
And what I see is the integral from minus infinity to infinity of e to the I kx dx is equal to 2 pi delta k. Now, by direct comparison, I have that relationship where my k is pm minus pn over h bar. So that means integral from minus infinity to infinity of e to the I pm minus pn over h bar x dx is equal to 2 pi delta of pm minus pn over h bar. Make sense?
Yep.
It's a whole lot easier doing it this way than it was trying to think it all the way through. One more thing. With that, now this is not a Kronecker delta, it's a Dirac delta. With that Dirac delta, when is Dirac delta not equal to 0?
Only at the delta.
Only at the argument equaling 0. So that means dividing by h bar isn't going to change anything, because it's still 0 divided by, it's still 0. So I can substitute this here for my integral So that's what I get when I apply that orthonormal relation what should the magnitude of this be if it's orthonormal? If it's normalized, what should the magnitude of this be? 1. So that means it should be just the Dirac delta Pm minus Pn. So that sets F0 mod squared times 2 pi is equal to 1. So F0 is equal to 1 over square root of 2 pi, where I took the positive real root. So we have our normalization condition. It's normalizable. But what's different about our orthonormal relationship here and what I wrote here? There's now only one difference. Go ahead.
Is it the type of delta that's different?
It's the time of delta. This was a Kronecker delta because I had discrete energy states. This here is a Dirac delta, here. A Dirac delta because it's continuous states. But it's still orthogonal, normalizable. If the momentum is any different, then we get 0. And so we still are obeying our orthonormal relationship. So it's a new odd kind of orthonormal relationship, hence my statement here. We find an interesting orthonormal variation. See how that worked? So the work I did here is outlined on page 103 of the textbook, but I had to go back and use that equation 2.144 for it to make sense. Otherwise, you just look at, it says referring to problems 2.24a and 2.26. That's what took me back to finding that relationship. But if you just look at equation 3.31 by itself, you have a hard time seeing how that worked out. So now what we found is our function for a given momentum as a function of x. So the eigenstate in x space for a given momentum is equal to 1 over square root of 2 pi. Oh, wait, I made a mistake. Where did I make that mistake? So suddenly I'm embarrassed. I lost my h bar when I did my normalization. I'm not gonna go try to figure out where I dropped it, but I dropped the h bar. It should have had an h bar in here. It could have been that. It could have been that. Yeah, I mean, yeah, if you look at their equation 331, it certainly looks like that is where it was. Right, because they have, it's equal to 2 pi h bar Dirac delta.
Because I think with Dirac deltas, whenever you multiply something,
it was one of our homework problems.
It comes outside.
Yeah, you're right. That was one of our homework problems. So I couldn't just divide it or just drop it. I had to bring it out. So there's our normalized wave functions, all of them. And then we have, the textbook shows just this next line, this. What does that mean? We're going to be using it a lot from now on. I want to make sure we know what that means. How do I expand that?
Okay, so that's the integral of the complex conjugate of fp prime times fp dx.
Right. It's important that you have that simply as something you know. You look at the nomenclature and you know it means this. Because we're going to use it a lot. And if you don't know what it means, you're going to be left off, There goes the bus, and I'm back here wondering, what did this even, I can't start the problem if I don't know what it means.
Right.
And so this relationship is our orthonormal relationship with the Dirac delta, because that's what we just did up here. So from what we learned before, and this is where we had Dirichlet's formula, we could take one function and put it in terms of another function just by saying that our new function is equal to a bunch of constants multiplied by each eigenstate. What that's saying is if I have a complete solution set, then I can take any function and write it as a linear combination of the complete solution set. So the C sub n's are the coefficients for each individual eigenstate to add up to give me my total function. And then we found C sub n by utilizing that relationship. So if you take this right here, the psi sub n, psi n is going to be integral because we have closed. And then the psi n, because it's the first thing, it's going to be psi star sub n. And then we have this f in the ket, which means that I'm going to put my function f, which is so this in parentheses is the function of x. And now I see I have a conflict in my indices, so let's just put m's. There. C sub m is equal to, that's an n, psi sub n star, and then f, where f is using m as a summing variable. But if you go through this is just an infinite number of integrals. And using the orthonormal relationship, that's not an n. This is rewriting what I just wrote by bringing the constant things out. The summation is not a function of x, and the C sub n is not a function, or yeah, C sub m is not a function of, C sub m is not a function of x. And what is this equal to?
The delta.
And this is the delta. It's the Kronecker delta in this case because I was doing discrete states. This is Dirichlet's relation here. And since that's delta nm, I have a summation for m equals 1 to infinity, but it's going to be 0 for everything except for when m is equal to n. And so that's why it gives us C sub n. Or if you really wanted, I could have written another step in here. I know you guys are far too astute to need this step. Summing all the C sub m's times delta mn, which is 0 unless m is equal to n. And so that was what we had before. Now we have a continuous function, though. So how are we going to do the same idea if it's a continuous function?
We're going to use the Dirac delta.
Yeah, it's pretty complicated, isn't it? Except for this is going to become an integral now because a summation is for discrete steps and an integral is for continuous. So we're going to have, and this is actually showing the full transformation here, but it's the same. I just skipped over the equation shown in the textbook. I skipped over because I didn't want to. Probably going to end early because I skipped over it, but it's okay. I have a problem to end. You know what? You take forever. Not you. I take forever doing quantum problems.
I don't know. It takes pretty long sometimes.
That's why we have the, quote, small problems on the test. If it wasn't a, quote, small problem, you would have had to actually find what the normalization constants were. But that would have taken you another, what, 2 hours?
Yeah, probably.
If it's all done for you, you can look at it in 30 seconds. But if you're doing the math, it's not a 30-second problem at all.
Right, exactly.
Okay, so here is using the transformations. You'll recognize where this comes from now, right? The F, yeah. The F sub P I forgot, of course, to put 1 over 2 pi. Let's just put it here. That's where it comes from. And here's the transformation from x space to momentum space, the top one. So here is psi as a function of x and time, and transforming it into phi as a function of momentum and time, or transforming from phi as a function of momentum and time into psi as a function of x and time. So you can transform. Yes, it is. Remember, it's just taking Dirichlet's formula or theorem, which was you can apply Fourier transform you can use a Fourier series to transform between momentum space and position space. And now for our example problem. A particle of mass m is bound in the delta function well Vx is equal to minus alpha dx. Once again, I did not notice this last night. Let me just rewrite the whole thing. That's the Dirac delta x, right? If you put d, it's not a delta function. That's a gloriously bad mistake there. And you can see here, it's, where is it? On page 10, the bottom of page 108 and top page 109 is where it is in the textbook, which you can see, yes, the delta function there is what I'm supposed to have. What's the probability that a measurement of momentum would yield a value greater than m alpha over h bar? Wow. Pretty impressive. So how do we start this thing?
I assume we have to find the momentum. That's the final we have to find the momentum states, I guess.
Yes. And to make sure that we follow why we have to do that, since you said I am assuming that was kind of a guess based on your feel.
Right. It's kind of trying to work backwards from where it's supposed to go and then steps back again.
So let's just think about how this would have been if we changed one thing. If we said, what's the probability of x greater than x0? How would you have found that? We actually did this very beginning of the class. Not today, but very beginning of the semester. What do we have that tells us about probabilities?
Well, we have psi mod squared.
Yes. Psi mod squared dx is probability of being between x and x plus dx. So if that's the probability of being between x and x plus dx, how do I find the probability of being greater than x0?
You can change your limits of integration.
Okay, I'm going to have to integrate. I didn't have an integral yet, so I can't change limits on a non-existent integral.
Well, I'm saying for the psi mod squared dx probability of being between x and x plus dx, you could say the probability between x naught and something bigger than that. Oh, okay.
Because it just says greater, then we could go all the way to infinity, right? That's how we would have done it before. But that's in position space. Now we're looking at momentum, so that's why Indy was right. We have to convert it to momentum space, and then we'll do exactly the same thing because we're just now in momentum space. So the first step, and the reason this problem is given here is for the conversion into momentum space, is going to be to convert this from position space to momentum space. So we have to look at our equation for converting, this one right here. And we're going to have and then I'm just going to multiply by my psi, so shrink down so I can see both at the same time. All righty. Okay, who wants to do this integral?
He does. So, yeah, but is x the only variable in there? There's a t in there. Yeah, but we're not integrating. Right, so we can get rid of all the constants. Yeah. Or all the things that aren't related to x. Can we pull out the e's, the IET over h bar?
I certainly believe we can.
And then
Because time is not affected by position.
Combine the exponentials.
Did I copy
Is there
that?
a reason why one is x and the other is yeah. Better question, do we even need that because we're only dealing with positive values? We don't know that. We're just dealing with values that go to.
Yeah, the momentum could be positive and negative. I think we could take out the e to the it over h bar.
Well, we're not integrating with respect to t. That's my philosophy. Are we starting at t equals 0? Is that like the pencil?
The T. I'm trying to think this through as I'm speaking. Speaking and thinking are mutually exclusive in my world. The time is not going to be dependent on position. Position is dependent on time, right? Because over time things are going to move. I think that it's legit to take it out, but I am not 100% confident suddenly. These lacks of confidence.
I mean, in the book, they pull it out.
Okay, that seems like a pretty good reason then to believe that I was right. A better one would be to be able to say, use mathematics to do it. The absolute value of x, how are we going to deal with the absolute value of x?
See, I feel like we should be able to combine those, but with that absolute value,
I'm trying to think of an easy, the book just says, oh, look, and that works out just fine. And I'm like, really? Good to know. It was too late at night for me to notice that I had something crazy. Notice what he said.
I looked up the integral.
I'm going to stick with that. I think last time I was looking, that's how I'm going to solve it. I looked up the integral by looking in my book. I kind of do appreciate his sense of humor in these things.
Yeah.
Because you know what you're going to have to do. You're going to have to break this up into two integrals. One integral that's from minus infinity to 0, and one that's from 0 to infinity. And that will allow you to get rid of the absolute value sign. And then you're going to have to complete the square for both of them. I think complete the square, and it's going to be real ugly. So following that lead, looking up the integral, oh boy, what does the integral come out to be? Something clearly ugly. Yeah. I am not going to try to separate it out.
All right, so why would they have a P and a P naught?
Okay, why is there a P and a P naught? Because, because the P0 is the momentum, I believe, when X is 0. That's what no, that doesn't make sense. You're right, that doesn't make sense.
The only thing I can think of with that logic, if it was at where x is equal to 0, would be from evaluating the integral from.
Back up. I do know why.
Okay.
It's because we have the problem defines P0 right here.
Yep.
And so we had this exponent here that was. That's where it came from.
Yeah. Right.
And so, when you combine the two, that's where it came into play. So here is our momentum space solution. And now we're able to do what we've already established. Our probability is equal to the integral from P0 to infinity of so we just take the mod squared of that. It's going to give us 2 pi as a constant, Notice the exponential term here is going to disappear because taking the complex conjugate. Well, P0 is a constant.
You can also pull P0 out.
Yeah, you're right with me. So there's our integral. Notice the 3/2 just became cubed because of the sum out squared, and it's divided by p squared plus p squared because of the two of them. So, once again, I know he says, I looked this one up too. Oh, again, I looked up the integral. Okay, go ahead.
Yeah, for this one, you're going to have to use trig substitution.
Yeah.
Right?
Yeah. And so it turns out that that's equal to, since he looked it up, and I'm trusting him to look it up, I'm also going to trust that he can put the limits in right. Right? Why distrust the man?
Yeah. Trust the man.
Okay. Yes, you're right. I always tell my students, you shouldn't trust me as the teacher. You should convince yourself that what I'm telling you is true. I'm convinced that Griffith wouldn't lie to me.
It's published.
Let me tell you, the textbook that I used to use for quantum, I really liked it, except for it was filled with errors. And some of them were pretty substantial, like when you're doing the hydrogen atom and you're finding the perturbation energy states, which we won't get to in this class. He's just got it all wrong. Not that he's mathematically wrong, it's in the substitution, it's substituted wrong. And the labels are wrong. And so in the next version, they tried to correct it, and it was wrong again, just differently. I like the textbook, but it is filled with errors, which makes it hard. I had to tell the students at the beginning, here's a list of errors. Here's errors that they've never corrected still. Anyway, so there's our answer, which if you put that in your calculator, assuming that David Griffith would never, it is David, right? Yes, would never lie to us. It's 0.0908 probability of it being higher than P0. What would it have been? Well, actually, that's position. It was the wrong question. Class ends right now, so I don't have to rephrase the question since it was the wrong question. I did send the email to Chris last night about setting up our time on Tuesday, and he's checking with the IS people there to see what they want to do. So the things are rolling. I know I waited until last night. I should have done it Wednesday night. But hopefully we'll have things set up so I can tell you on Monday. And
Right, cool.
I will get you a homework assignment up soonish.
Okay.
And get you a graded test soonish too. Right.
Yeah.
Have a happy Sabbath.
All right, thank you. Have a good weekend.
Thank you.